So for IR, so infrared radiation will bend, vibrate, stretch, stretch bonds, but not break them. Right? Nothing breaks. In mass spec, bonds broke. In IR, bonds don't break. All right. Oh, all bonds are different. So they will bend, stretch in a characteristic manner. Based on the type of bonds they are. Right? So will alkyne CH vibrate differently than a sp3CH? Yeah. Will a CCl bond vibrate or stretch differently than a CBr bond? Yeah. Will a carbon-carbon alkene, a CC double bond, vibrate differently than a CC single bond? Yeah. Will CO bond vibrate differently than a CN bond? Yeah. So that's all IR tells us about functional groups. Right? So it tells us functional groups. All right, this tells us the functional groups based on how the bonds, right, interact with the infrared light. There's no reactions, just an interaction. No bonds are breaking, we're just stretching and bending bonds. Okay, rule of 13. Let's look at number 9 in your homework. It's from chapter 14. So number 9, the homework wants to know the molecular formula of the alkane. So it's CNHX. So if it's an alkane, what does that automatically tell us? What hybridization state are all the carbons? They're all sp3. So it's all sp3 carbons. And that means, do we have any pi bonds? No pi bonds. And the mass spec is shown, and it says, here, actually for this one, for number 9, it has the molecular ion is 100. So the molecular ion is 100. That means that's the largest peak, or the largest fragment. That just means the molecule minus an electron. So the rule of 13, then, to help us figure out this molecular formula, we take 100 divided by 13, which of course is. So again,
wait, is it an abundance? Or
100 is the molecular ion.
Oh, okay.
All right,
It's
so
the
that's
highest one on the chart.
That's the highest one on the spectrum. Yep, that's the largest fragment on the spectrum. So it's the whole molecule that's minus 1 electron. All right. So we can get there. You see that's 7 times, right? So 7 times 13 is 91, right? So that's telling us there's 7 carbons. And to figure out how many H's there are, we take 7 plus 100 minus 91, which is 9, right? And 7 plus 9 is 16. So there's 16 hydrogens.
Isn't the same thing as like 7 times 2 plus 2?
Okay. All right, so let's look at number 4 in chapter 14. Welcome back, David. So the first thing I'm going to do for number 4 is draw the molecule. Oh man. So the question says, give the parent compound, draw the mass spectrum fragment that is observed at mass to charge ratio 77, include any hydrogen atoms and the charge. All right. So what do we need to do first? What's the first thing that's going to happen with this molecule?
What's the beam?
The electron beam, right? The electron beam is going to hit. And what electron is the easiest to knock out? Or what type of electron is easiest to knock out here? One of the electrons on the chlorine, right? So dot, all of a sudden now we have a plus. All right, so now the chlorine has a plus charge. Is the chlorine happy having a plus charge? No. So what are the two ways, right? There's two ways these types of molecules can break up. We talked about in class. They can break up heterolytically or homolytically. Which way is more likely with chlorine having a plus charge? What's the difference between, what's a heterolytic cleavage mean?
2 electrons.
2 electrons moving. Homolytic means 1 electron. Does chlorine want to have a plus charge? No. So, would you think chlorine's more likely to take the 2 electrons than just mess around with just getting 1 more? It's going to take the 2. Right? Double arrow, heterolytic cleavage, right? Okay. Now, the problem asks, draw the mass spectrum for the fragment that is observed at mass to charge 77. So we're looking for something that weighs, right, the number of carbons and hydrogens and what else is on there weighs 77. But it also has to have what else on it? For the mass spec to see it, what must it have on it? What else must it be? Positively charged, right? It has to be positively charged. So after I move these arrows, right? So I just move these arrows here. The chlorine has got 2 electrons, right? Who just lost 2 electrons? This carbon right here, right? The carbon that the chlorine is connected to. Will that carbon have a charge now? Right. It'll now have a what charge? Positive charge. Good. And we'll have a chlorine that no longer has a plus charge, but how many electrons does the chlorine have around it now? 7. Right, which is how many electrons chlorine normally has, right? It's its valence shell, which is better than having a plus charge.
But I thought 2 electrons moved.
They did.
Because one's already sharing with the carbon.
Right. So look here, right? So chlorine had 1 electron, 2, 3, 4, 5,
Oh, it
6, 7. It takes both,
Okay.
right? And this carbon here lost a bond. Now the tricky part here is when we want to read the directions, right? So it says, give the parent compound, draw the mass spectrum fragment that is observed for mass charge 77. First thing we want to check is, does this compound this plus charge compound we made, is this mass 77? If you add up all the carbons, it's benzene. So it's how many carbons? 6. 6 times 12. 72. And it also asks us to draw in the hydrogens, right? So there's an H here, an H here, an H here, an H here, and an H here. Notice, right, there was no H bonded here, right? So we don't add an H in. In mass spec, we break bonds, right? We don't make bonds, we break bonds, right, usually. All right, so one of the key parts people probably mess up on is not just putting a plus charge here, but they also probably forget to draw in the H's. All right, so this is that heterolytic cleavage. All right, so let's look at number 5 from chapter 14. So this problem asks, it says, give the parent compound, draw the mass spectrum fragment that is observed at mass of charge 71, include any hydrogen atoms and the charge. So they start off with this compound. What's this compound called? 1, 2, 3, 4, 5, 6, 7. We call this one Heptane, good.
I was gonna say
Heptane. Our heptane, we submit the heptane to the electron beam, right? What is what's the first thing that happens? We lose just one electron, right? The problem with these hydrocarbons, I don't know where the one electron left from, right? So if I don't know where it's coming, where it's leaving, I have to put a dot plus like this to show this molecule is just down one electron.
So what's the little like upside down valve?
That's just a bracket,
Oh. Oh,
right? So what does heptane weigh? What's the molecular weight of heptane? 6 times 7,
Or wait, no,
80,
7 times 12, right?
7 times 12, which of course would be
84.
84. 84. How many hydrogens are there now?
96.
Max saying 96 total?
Yeah.
Okay, I'm believing Mac. We'll say this whole thing weighs 96, which is
95 without with the.
I didn't lose any hydrogens though.
Oh, okay.
So it's still 96, I think.
Yep.
So it weighs 96, right? The molecular ion is 96. But the problem is they want us to draw the mass spectrum fragment that is observed for massive charge 71. So what bond would we need to break to form a fragment that weighs 71? So if I number the carbons, 1, 2, 3, 4, 5, 6, 7, I need to get a molecule, a fragment that weighs 71. Max saying, what's one way to look at this? A quick way to do this is say, well, if it weighs 96, I'm trying to get to 71, the size of the fragment I have to lose is what? 25, right? So what bond would I need to break? I need to lose 2 carbons, right?
5 and 6.
Are we sure the mass weighs 96?
It's not.
I think we need to back up the 96 train.
I think it's more.
I think it has to be more, right? This is a good lesson to see, though, right? So it has to be more.
I need a calculator.
Okay, so we're back. This is wrong. It's 100. This idea still holds true, though. What's 100
And so the
minus 71 is 29. So we need to have one fragment that weighs 71 and one fragment that weighs 29. So which bond could we break here? We could break the bond between 2 and 3. The tricky part is coming up. That might have been the adding the carbons plus the hydrogens might have been the tricky part. But now they're saying we see a fragment at 71. So all the fragments we see have to have what charge? Plus charge. So which one of these fragments is going to have the plus charge? And one's going to have a plus charge and one's going to have the radical, right? The dot. So the big one's going to have the plus. I think carbon 3. And then carbon 2 is going to have the dot.
why does the big one have a plus charge?
Because they're telling us we see a fragment at 71. So the only fragments we see are the plus charge fragments. Okay, let's do an alpha cleavage practice problem. Let's do it with, what halogen do you guys want to use? Bromine. So the best thing to do with all these is to draw in the lone pair electrons always first, I think. All right? So the first thing that happens if we put this 2-bromo-propane into a mass spec, right? We have the electron beam, which, of course, does what? Kicks out an electron, right? So we get a dot and then a plus charge where the one electron was at. All right? We've already talked about one way this can break up. And one way this can break up is in a heterolytic fashion, right? So still look at that. So what happens here is both these electrons go with the bromine. So heterolytic cleavage means we're losing 2 electrons at a time. Right, double-headed arrow. And that product's going to look like right? The bromine got the 2 electrons, now it has 7 electrons around it. And we have to remember to put the plus charge on that carbon. So what weight fragment, what mass to charge ratio would we expect for a heterolytic cleavage in this case? What mass would we expect in this case for this one? Be 3 carbons. How many hydrogens? Draw the hydrogens in if you're not sure. We have 3 carbons and how many hydrogens? There's 6, at least 6. How many hydrogens were on this carbon? Just the 1.
43.
All right, so it's going to weigh 12 times 3, 36. And there's how many hydrogens? 7?
44.
I think it's 43.
It is.
43. Okay. All right, we all can agree that fragment weighs 43. So would we expect in the mass spec to see a peak that weighs 43? Yes. But that's not the only peak we'd see. All right, let's redraw. I'm going to redraw this over here to show another pathway, right? Another pathway that this can break up called alpha cleavage. All right? Alpha cleavage. So what alpha cleavage means is essentially a bond that is attached to the carbon that's alpha to the bromine, right? So this carbon is technically alpha here, right? This bond right here is going to break. And it's a homolytic cleavage, which means we're moving 1 electron at a time, right? We're moving 1 electron at a time. So I think the easiest way to see this is to maybe draw the products in first. So I'll draw the products in down here. So the products are going to look like, also it's probably easier to number these carbons, 1, 2, 3. So we're going to end up with a CH3 with a dot, and this is carbon 1. We're also going to have, I'm just going to build a line there, a bromine with a plus charge that has a new pi bond to carbon 2. And there's carbon 3 still there. So now we got to draw arrows to indicate how we form these products. Right? So we know what bonds broke. What bond broke? Between 1 and 2, right? So one of these electrons is going to go to carbon 1. Notice the fish hook. Only moving 1 electron when I do that arrow. But we also realize, right, we formed a new pi bond. How many electrons in a pi bond? 2. Did the bromine lose one of its? Looks like this radical is on the bromine is no longer there. So this electron went towards there to be part of that new forming pi bond. And the other electron from between carbon 1 and 2 also joined up and became part of that pi bond. So those were the 2 electrons, right? And these are the 2 electrons that formed this pi bond. And the 1 electron is over here now. That's called an alpha cleavage.
Are they always double bond or is
You always will form a pi bond and a radical.
How did you know it was alpha carbon?
How do I know what is the alpha carbon? Right, so whatever the carbon, so this is the carbon the bromine's attached to.
Right.
The one away from the where it's attached to is called the alpha carbon.
You could have picked 1 or 3.
1 or 3 would have been fine here.
Okay.
Yep, 1 or 3 would have been fine here.
Wait, is it CH3 with a positive charge or is it
CH3 with a
plus?
CH3 with a dot, right? Because the plus charge stays in the bromine. Right? Because all this carbon got was one radical, 1 electron there.
So that's a dot now, right?
So that's a dot. Sorry, here, let me make it better. This is a dot.
Not in the line. Oh, okay.
That is a dot, not a line. Very good. So the how do we decide which one of these is more likely to happen? So which one do we think is more likely to happen? A heterolytic cleavage, right up here, or an alpha cleavage here? Which one do we think is more likely to happen? Why would a heterolytic is more likely to happen? Why?
Because the carbon, their secondary is more stable.
Because we'd rather have a carbon with a plus charge or a bromine with a plus charge. Right. So it's not to say this happens, but it's not going to happen as often as this, right? So which peak would be higher in the mass spec? This one would be the 43 peak. Because what would this one weigh? This is gonna be tough. Oh boy. What is this one gonna weigh? Okay, so to find the mass, we need to remember we have an H here. But remember, there's still an H on carbon 2. Don't forget there's still an H on carbon 2. That is still there. So we had 24 for the carbons. There's 2 carbons. There's 4 H's. And then 79 for the bromine, which comes to 107. But there's also a peak at 109. What does the peak at 109 represent? Bromine has an isotope at 81. And it's a 1-to-1 ratio. So we'd expect to see 2 peaks, equal intensity, equal abundance at 107 and 109 because bromine has 2 different isotopes naturally occurring in a 50-50 ratio in nature.
Is it always like 79, 81 for that 101?
There's 2 bromine isotopes, 79 and 81.
Yeah.
So we always have 2. If the bromine's in the molecule, you always see that 1-to-1 ratio in those peaks. But again, you'd still see a peak at 43 that'd probably be bigger.